Chapter 2. The Electricity of Chemistry. A more tractable kind of electricity than that of friction was discovered at the beginning of the present century. The story goes that some edible frogs were skinned to make a soup for Madame Galvani, wife of the professor of anatomy at the University of Bologna, who was in delicate health. As the frogs were lying in the laboratory of the professor, they were observed to twitch each time a spark was drawn from an electrical machine that stood by. A similar twitching was also noticed when the limbs were hung by copper skewers from an iron rail. Galvani thought the spasms were due to electricity in the animal, and produced them at will by touching the nerve of a limb with a rod of zinc, and the muscle with a rod of copper in contact with the zinc. It was proved, however, by Alessandro Volta, professor of physics in the University of Pavia, that the electricity was not in the animal, but generated by the contact of the two dissimilar metals and the moisture of the flesh. Going a step further, in the year 1800 he invented a new source of electricity on this principle, which is known as Voltas Pile. It consists of plates or discs of zinc and copper, separated by a wafer of cloth moistened with acidulated water. When the zinc and copper are joined externally by a wire, a current of electricity is found in the wire. One pair of plates with the liquid between makes a couple or element, and two or more, built one above another in the same order of zinc, copper, make the pile. The extreme zinc and copper plates, when joined by a wire, are found to deliver a current. This form of the voltaic, or as it is sometimes called, galvanic battery, has given place to the cell shown in figure 11, where the two plates ZC are immersed in acidulated water within the vessel, and connected outside by the wire W. The zinc plate has a positive and the copper a negative charge. The positive current flows from the zinc to the copper inside the cell, and from the copper to the zinc outside the cell, as shown by the arrows. It thus makes a complete round, which is called the Voltaic Circuit, and if the circuit is broken anywhere it will not flow at all. The positive electricity of the zinc appears to traverse the liquid to the copper, from which it flows through the wire to the zinc. The effect is that the end of the wire attached to the copper is positive, plus, and called the positive pole or electrode, while the end attached to the zinc is negative, minus, and called the negative pole or electrode. A simple and easy way to avoid confusion as to the direction of the current is to remember that the positive current flows from the copper to the zinc at the point of metallic contact. The generation of this current is accompanied by chemical action in the cell. Experiment shows that the mere contact of dissimilar materials, such as copper and zinc, electrifies them, zinc being positive and copper negative. But contact alone does not yield a continuous current of electricity. When we plunge the two metals still in contact, either directly or through a wire, into water preferably acidulated, a chemical action is set up, the water is decomposed, and the zinc is consumed. Water, as is well known, consists of oxygen and hydrogen. The oxygen combines with the zinc to form oxide of zinc, and the hydrogen is set free as gas at the surface of the copper plate. So long as this process goes on, that is to say, as long as there is zinc and water left, we get an electric current in the circuit. The existence of such a current may be proved by a very simple experiment. Place a penny above and a dime below the tip of the tongue, then bring their edges into contact, and you will feel an acid taste in the mouth. Figure 12 illustrates the supposed chemical action in the cell.
On the left hand are the zinc and copper plates ZC disconnected in the liquid. The atoms of zinc are shown by small circles, the molecules of water, that is oxygen and hydrogen H2O, by lozenges of unequal size. On the right hand the plates are connected by a wire outside the cell. The current starts and the chemical action begins. An atom of zinc unites with an atom of oxygen, leaving two atoms of hydrogen thus set free to combine with another atom of oxygen, which in turn frees two atoms of hydrogen. This interchange of atoms goes on until the two atoms of hydrogen which are freed last abide on the surface of the copper. The contact electricity of the zinc and copper probably begins the process, and the chemical action keeps it up. Oxygen, being an electronegative element in chemistry, is attracted to the zinc, and hydrogen, being electropositive, is attracted to the copper. The difference of electrical condition or potential between the plates by which the current is started has been called the electromotive force, or force which puts the electricity in motion. The obstruction or hindrance which the electricity overcomes in passing through its conductor is known as the resistance. Obviously, the higher the electromotive force and the lower the resistance, the stronger will be the current in the conductor. Hence it is desirable to have a cell which will give a high electromotive force and a low internal resistance. Voltaic cells are grouped together in the mode of Leyden jars. Figure 13 shows how they are joined in series, the zinc or negative pole of one being connected by wire to the copper or positive pole of the next. This arrangement multiplies alike the electromotive force and the resistance. The electromotive force of the battery is the sum of the electromotive forces of all the cells, and the resistance of the battery is the sum of the resistances of all the cells. High electromotive forces or pressures capable of overcoming high resistances outside the battery can be obtained in this way. Figure 14 shows how the zincs are joined in parallel, the zinc or negative pole of one being connected by wire to the zinc or negative pole of the rest, and all the copper or positive poles together. This arrangement does not increase the electromotive force, but diminishes the resistance. In fact, the battery is equivalent to a single cell, having plates equal in area to the total area of all the plates. Although unable to overcome a high resistance, it can produce a large volume or quantity of electricity. Numerous voltaic combinations and varieties of cell have been found out. In general, wherever two metals in contact are placed in a liquid which acts with more chemical energy on one than on the other, as sulfuric acid does on zinc in preference to copper, there is a development of electricity. Readers may have seen how an iron fence post corrodes at its junction with the lead that fixes it in the stone. This decay is owing to the wet forming a voltaic couple with the two dissimilar metals and rusting the iron. In the following list of materials, when any two in contact are plunged in dilute acid, that which is higher in the order becomes the positive plate or negative pole to that which is lower. Positive: zinc, cadmium, tin, lead, iron, nickel, bismuth, antimony, copper, silver, gold, platinum, graphite. Negative. There being no chemical union between the hydrogen and copper in the zinc and copper couple, that gas accumulates on the surface of the copper plate or is liberated in bubbles. Now, hydrogen is positive compared with copper, hence they tend to oppose each other in the combination. The hydrogen diminishes the value of the copper, the current grows weaker, and the cell is said to polarize. It follows that a simple water cell is not a good arrangement for the supply of a steady current. The Daniell cell is one of the best, and gives a very constant current. In this battery the copper plate is surrounded by a solution of sulphate of copper, CuSO4, which the hydrogen decomposes, forming sulphuric acid, H2SO4, thus taking itself out of the way and leaving pure copper, Cu, to be deposited as a fresh surface on the copper plate. A further improvement is made in the cell by surrounding the zinc plate with a solution of sulphate of zinc, ZnSO4, which is a good conductor. Now, when the oxide of zinc is formed by the oxygen uniting with the zinc, the free sulphuric acid combines with it, forming more sulphate of zinc and maintaining the conductivity of the cell. It is only necessary to keep up the supply of zinc, water, and sulphate of copper to procure a steady current of electricity. The Daniell cell is constructed in various ways. In the earlier models the two plates with their solutions were separated by a porous jar or partition, which allowed the solutions to meet without mixing, and the current to pass. Sawdust moistened with the solutions is sometimes used for this porous separator, for instance on board ships for laying submarine cables, where the rolling of the waves would blend the liquids. In the gravity Daniell, the solutions are kept apart by their specific gravities, yet mingle by slow diffusion. Figure 15 illustrates this common type of cell, where Z is the zinc plate in a solution of sulphate of zinc, and C is the copper plate in a solution of sulphate of copper, fed by crystals of the blue vitriol. The wires to connect the plates are shown at WW. It should be noticed that the zinc is cast like a wheel to expose a larger surface to oxidation, and to reduce the resistance of the cell, thus increasing the yield of current. The extent of surface is not so important in the case of the copper plate, which is not acted on, and in this case is merely a spiral of wire, helping to keep the solutions apart and the crystals down. The Daniell cell is much employed in telegraphy. The Bunsen cell consists of a zinc plate in sulphuric acid and a carbon plate in nitric acid, with a porous separator between the liquids. During the action of the cell, hydrogen, which is liberated at the carbon plate, is removed by combining with the nitric acid. The Grove cell is a modification of the Bunsen, with platinum instead of carbon. The SME cell is a zinc plate side by side with a platinized silver plate in dilute sulphuric acid. The silver is coated with rough platinum to increase the surface and help to dislodge the hydrogen as bubbles and keep it from polarizing the cell. The Bunsen, Grove, and SME batteries are, however, more used in the laboratory than elsewhere. The Leclanche is a fairly constant cell which requires little attention. It polarizes in action, but soon regains its normal strength when allowed to rest, and hence it is useful for working electric bells and telephones. As shown in figure 16, it consists of a zinc rod with its connecting wire Z and a carbon plate C with its binding screw between two cakes MM of a mixture of black oxide of manganese, sulfur, and carbon plunged in a solution of sal ammoniac. The oxide of manganese relieves the carbon plate of its hydrogen. The strength of the solution is maintained by spare crystals of sal ammoniac lying on the bottom of the cell, which is closed to prevent evaporation, but has a vent hole for the escape of gas. The bichromate of potash cell polarizes more than the Leclanche, but yields a more powerful current for a short time. It consists, as shown in figure 17, of a zinc plate Z between two carbon plates CC immersed in a solution of bichromate of potash, sulphuric acid, vitriol, and water. The zinc is always lifted out of the solution when the cell is not in use. The gas which collects in the carbons and weakens the cell can be set free by raising the plates out of the liquid when the cell is not wanted. Stirring the solution has a similar effect, and sometimes the constancy of the cell is maintained by a circulation of the liquid. In Fuller's bichromate cell, the zinc is amalgamated with mercury, which is kept in a pool beside it by means of a porous pot. De la Rue's chloride of silver cell, figure 18, is, from its constancy and small size, well adapted for medical and testing purposes. The plates are a little rod or pencil of zinc, Z, and a strip or wire of silver, S, coated with chloride of silver and sheathed in parchment paper. They are plunged in a solution of ammonium chloride, A, contained in a glass phial or beaker, which is closed to suppress evaporation. A tray form of the cell is also made by laying a sheet of silver foil on the bottom of the shallow jar and strewing it with dry chloride of silver, on which is laid a jelly to support the zinc plate. The jelly is prepared by mixing a solution of chloride of ammonium with agar-agar or Ceylon moss. This type permits the use of larger plates and adapts the battery for lighting small electric lamps. Skrivanov has modified the de la Rue cell by substituting a solution of caustic potash for the ammonium chloride, and his battery has been used for star lights, that is to say, the tiny electric lamps of the ballet. The Sheath Battery, consisting of zinc and carbon plates in a solution of basic sulphate of mercury, is suitable for reading, mining, and other portable lamps. The Latimer Clark standard cell is used by electricians in testing as a constant electromotive force. It consists of a pure zinc plate separated from a pool of mercury by a paste of mercurous protosulfate and saturated solution of sulfate of zinc. Platinum wires connect with the zinc and mercury and form the poles of the battery, and the mouth of the glass cell is plugged with solid paraffin. As it is apt to polarize, the cell must not be employed to yield a current, and otherwise much care should be taken of it. Dry cells are more cleanly and portable than wet. They require little or no attention and are well suited for household or medical purposes. The zinc plate forms the vessel containing the carbon plate and chemical reagents. Figure 19 represents a section of the ECC variety, where Z is the zinc standing on an insulating sole I, and fitted with a connecting wire or terminal T minus, which is the negative pole. The carbon C is embedded in black paste M, chiefly composed of manganese dioxide, and has a binding screw or terminal T plus, which is the positive pole. The black paste is surrounded by a white paste Z, consisting mainly of lime and sal ammoniac. There is a layer of silicate cotton SC above the paste, and the mouth is sealed with black pitch P, through which a waste tube WT allows the gas to escape. The Hellesen dry cell is like the ECC, but contains a hollow carbon and is packed with sawdust in a millboard case. The Leclanche-Barbier dry cell is a modification of the Leclanche wet cell, having a paste of sal ammoniac instead of a solution. All the foregoing cells are called primary because they are generators of electricity. There are, however, batteries known as secondary, which store the current as the Leyden jar stores up the discharge from an electrical machine. In the action of a primary cell, as we have seen, water is split into its constituent gases, oxygen and hydrogen. Moreover, it was discovered by Carlisle and Nicholson in the year 1800 that the current of a battery could decompose water in the outer part of the circuit. Their experiment is usually performed by the apparatus shown in figure 20, which is termed a voltameter, and consists of a glass vessel V containing water acidulated with a little sulphuric acid to render it a better conductor, and two glass test tubes OH inverted over two platinum strips or electrodes, which rise up from the bottom of the vessel and are connected underneath it to wires from the positive and negative poles of the battery CZ. It will be understood that the current enters the water by the positive electrode and leaves it by the negative electrode. When the power of the battery is sufficient, the water in the vessel is decomposed, and oxygen being the negative element, collects at the positive foil or electrode, which is covered by the tube O. The hydrogen, on the other hand, being positive, collects at the negative foil under the tube H. These facts can be proved by dipping a red-hot wick or taper into the gas of the tube O, and seeing it blaze in presence of the oxygen which feeds the combustion. Then dipping the lighted taper into the gas of the tube H, and watching it burn with the blue flame of hydrogen. The volume of gas at the cathode, or negative electrode, is always twice that at the anode, or positive electrode, as it should be according to the known composition of water. Now, if we disconnect the battery and join the two platinum electrodes of the voltameter by a wire, we shall find a current flowing out of the voltameter as though it were a battery, but in the reverse direction to the original current which decomposed the water. This secondary or reacting current is evidently due to the polarization of the foils, that is to say, the electropositive and electronegative gases collected on them. Professor Groves constructed a gas battery on this principle, the plates being of platinum and the two gases surrounding them oxygen and hydrogen, but the most useful development of it is the accumulator or storage battery. The first practicable secondary battery of Gaston Plante was made of sheet lead plates or electrodes kept apart by linen cloth soaked in dilute sulphuric acid, after the manner of Voltas Pile. It was charged by connecting the plates to a primary battery, and peroxide of lead, PbO2, was formed on one plate, and spongy lead, Pb, on the other. When the charging current was cut off, the peroxide plate became the positive and the spongy plate the negative pole of the secondary cell. Faure improved the Plante cell by adding a paste of red lead or minium, Pb2O4, and dilute sulphuric acid, H2SO4, by which a large quantity of peroxide and spongy lead could be formed on the plates. Celan and Volckmar increased its efficiency by putting the paste into holes cast in the lead. The EPS accumulator of the Electrical Power Storage Company is illustrated in figure 21, and consists of a glass or teak box containing two sets of leaden grids perforated with holes, which are primed with the paste and steeped in dilute sulphuric acid. Alternate grids are joined to the poles of a charging battery or generator, those connected to the positive pole being converted into peroxide of lead and the others into spongy lead. The terminal of the peroxide plates, being the positive pole of the accumulator, is painted red, and that of the spongy plates or negative pole black. Accumulators of this kind are highly useful as reservoirs of electricity for maintaining the electric light, or working electric motors in tramcars, boats, and other carriages. End of chapter 2.